Hey guys, welcome back to another video. In this lesson, we'll look to consolidate what we learnt about momentum, and we'll take a look at some questions. I've got the equations at the top of the page, which we'll use as reference, so let's get stuck into it. I think a good place to start with all these types of questions is with a diagram. So let's actually draw one out as we read the question. So we're presented with a snooker ball, which travels with a velocity of 11 meters per second towards the left. So I will go ahead and draw that as a blue snooker ball, and we'll give it a velocity, and we'll call this snooker ball A. So we'll say VA initially is traveling at 11 meters per second. And it collides with a stationary ball, and I will make that ball pink and call that ball B. So it's stationary, so I'll say VB initially is equal to 0 meters per second. And we've also been given the masses, so I'll go ahead and put that in. So we'll say mass of A is equal to 150 grams, so 1.15 kilograms. And the mass of B is given as well as 200 grams. So let's put that in. Mass of B is equal to 200 grams, which is 0.2 kilograms. So I'll call this situation our initial picture, so initial condition. And then it says that if the final velocity of the ball weighing 150 grams, so ball A, is 3 meters per second to the left, let's find the velocity of the stationary ball after the collision. So a collision takes place, so let's draw that condition as well. My assumption is that because A has hit B towards the left, then B will also start moving with some velocity, but we just don't know what it is. So let's label that. So let's say VB is now, this is the final condition, VBF. So that's what we have to find out. The mass of B is still 0.2 kilograms. It's not like there's been any loss of mass here, so that's B. And VA is going to be moving with a velocity of 3 meters per second. So now VB has been hit by VA, so VA final is going to be equal to 3 meters per second. And our mass is, of course, going to remain the same. So mass of A is 150 grams, which is 0.15 kilograms. And let's label this the after condition, and I will write that in a different color so we don't confuse ourselves. After. Now, if we think about this problem within the context of the law of conservation of momentum, we know that the momentum in the initial condition must be equal to the momentum in the after condition. And as we went through before in our previous lesson, I like to think of it as taking two pictures at different points in time and calculating the momentum in both of those pictures. So we have our initial picture, which I've taken before the collision happens, and we have our after picture that we've just drawn as well. So let's go ahead and apply the conservation of momentum over here, the law of conservation of momentum. And we can use that to say the sum of all the momentum in the initial condition is equal to the sum of all the momentum in the final condition. And a little bit of an interesting tidbit is that we use P to signify momentum instead of M, because M obviously already signifies mass. Before we go ahead and plug our values in, we do need to assign what direction is going to be positive. And it looks like our masses are probably going to be moving towards the left, so I will assign my left direction as positive. So now that we've got a direction going, let's go ahead and put in our values. So the momentum in the initial condition is going to be the momentum of A plus the momentum of B. So let's write that down mathematically. So we're going to say P of A plus P of B, and this is in the initial condition, so I'll put I's back in there. It's going to be equal to P of A plus P of B in our final condition. Our P of A is going to be mass of A times the velocity of A. And because this will be the initial condition that we're looking at for A, we'll put an I on V, and the masses will obviously remain constant throughout. Then we'll go ahead and look at our P of B, the momentum of B terms, and that'll be M of B times VBI. We'll go ahead and do a similar thing to the right side. So the momentum of A in the final condition is just MA times VA final. Similarly for B, it'll be MB VB final. So let's scroll up a bit and get those values from our diagram. We know MA is 0.15, so I can plug that in, 0.15. And we know the initial velocity of A is 11 to the left, so that V will remain positive in our equation. And in our initial condition, our velocity of B is 0 because the snooker ball is stationary. So let's go ahead and put that in. So MB is 0.2 times 0 velocity. And in the final condition, we have MA traveling at 3 meters to the left still. So the mass is still 0.15, and this is 3. And what we need to find out is the final velocity. So that's going to be our unknown. So our mass of B is 0.2, and what we need to find is VBF. So we know this term is going to go to 0 because anything times 0 is equal to 0. Let's go ahead and multiply these other numbers out. So if I put these numbers into the calculator, I get this to be 1.65. So we have 1.65, and this becomes 0.45 plus 0.2 VBF. So we can go ahead and transpose this for VBF. So VBF is equal to 1.65 minus 0.45 divided by 0.2, which gives me a value of VBF is equal to 6 meters per second. And because we've got a positive here, we know that VB will continue moving towards the left. So we'll say 6 meters per second toward the left. So let's go ahead and move on to our next question. And this is actually a question I think I came across in a previous exam. I'm not entirely sure which year it was, but essentially what's going on here is that there's a car with a mass of 1,200 kilograms, and this car is on a direct collision course with a truck which is stationary, and the mass of the truck is 2,200 kilograms. So I'll go ahead and write this as my before condition. So my before condition, which I'll just write as initial, so initial condition. And we see that after the collision, the truck starts to move towards the right at 6.5 meters per second. And the first thing we're asked here is, what is the velocity of the car after this collision has taken place? So let me write this second condition as our after condition. So we know our before picture, we know our after picture, so we can go ahead and use the law of conservation of momentum and calculate the momentum in both of these pictures. So we can say the mass, the momentum of all the stuff that's happening before, so initial is equal to the momentum in the after condition. Or final, that should really just be final, just so we're consistent. So I'll change that A to an F. Let's go with final. So let's write out our terms. So we want to know the momentum of the car plus the momentum of the truck initially is going to equal to the momentum of the car plus the momentum of the truck in our final condition. So these can be expanded out into their constituents. So momentum of car is just the mass of the car times the velocity of the car initially plus the mass of the truck multiplied with the velocity of the truck initially. And that's going to equal to the mass of the car times the velocity of the car in our final condition plus the momentum of the truck, which is the mass of the truck times velocity of the truck in our final condition. So we can move ahead and plug our numbers in. But before we do, we always have to assign a direction, which is positive. And my assumption is because this car is going to be moving towards the right when it hits the truck is also going to move towards the right with the car at the end. So let's make our right as positive. And let's go ahead and plug these values into the equation down here. So the mass of the car is 1,200 kilograms. The velocity of the car initially is 10 meters per second, so I'll put that in. The mass of the truck is going to be 2,200 kilograms, and the velocity of the truck is 0. The mass of the car at the end is still going to be the same in the final condition, so 1,200. The velocity of the car is what we need to find out, so VCF, our final velocity for the car. The mass of the truck is going to remain the same. There's no loss in mass here, so 2,200 kilograms. And we know the velocity of the truck is going to be 6.5 at the end, meters per second towards the right. So the velocities stay positive because obviously we've assigned right as positive. So let's go ahead and plug these numbers into our equation, into our calculator rather. So 1,200 times 12 is 12,000. So that's all the momentum on the left side of the equation, or in our initial condition. And that's going to be equal to 1,200 times our unknown velocity of the car, which is VCF, plus 2,200 times 6.5, which is the momentum of the truck. So that's going to be equal to 14,300. So let's go ahead and solve this for VCF. So we've got 12,000 minus 14,300 divided by 1,200 to give us VCF, and VCF will therefore equal negative 1.92 meters per second. And this negative just signifies that the car would initially travel in the right direction and rebound off the truck and go the other way in the left direction. So our VCF is just 1.92 meters per second, where this negative specifies our direction, which is left. Now the second part of this question actually asks us if this collision is elastic or inelastic. And if we go back to our previous lesson, we learnt that an elastic collision is one where the kinetic energy before the collision is equal to the kinetic energy after the collision. So we can go ahead and write that down as an equation. So we can say the sum of all the kinetic energy before, so initially, is equal to the kinetic energy after the collision. So that's final, or little f, doesn't really matter. And we know that the formula for kinetic energy is just equal to half mv squared. So I'll put that on the side just for reference, half mv squared. So let's go ahead and calculate our kinetic energies for both of these scenarios. So we've got the kinetic energy of the car initially plus the kinetic energy of the truck initially, and that's going to be equal to the kinetic energy, or at least we want to prove if it is elastic, it should equal the kinetic energy of the car in our final condition plus the kinetic energy of our truck in its final condition. Then we can go ahead and substitute this formula in, so we can say half mass of the car times the velocity initially squared plus half mass of the truck, and that's initially for the car, so car initially, mass of the truck times velocity of the truck initially squared is going to be equal to half mc VC final squared plus half MT VT final squared. So then let's go ahead and put in our values. So we've got half times the mass of the car, which is 1200, multiplied with the initial velocity of the car, which is equal to 10 meters per second, and that'll be squared, plus half times the mass of the truck, which is 2200, times the velocity of the truck, which was 0, and that'll be squared. And that's going to be equal to a half times the mass of the car again, which is 1200, times the velocity, which we worked out to be negative 1.92, but the square of a negative is just going to be a positive, but I'll put a negative in there because it's good practice. And we'll go plus mass of the truck again, which is 2200, multiplied by the velocity, which is 6.5. And I will move that down so it's a bit easier to read. So that'll be 6.5 squared. And if I put these values into the calculator, I get a kinetic energy in the initial condition, which is going to be 60 kilojoules, or 60,000 joules, whatever you're more comfortable with. And that's because the truck initially will have 0 velocity, so this term will go to 0. And if we want to make sure that this is an elastic collision, we have to make sure that the left side, so the initial condition, the kinetic energy in the initial condition is equal to the kinetic energy in the final condition. So let's go ahead and work the right side out as well. So this is our initial KE. And now we're going to go ahead and work out our final KE. So if I plug these values into a calculator, what I get is 48.7 kilojoules for our final condition, so our final KE. So because we have our initial KE, so the sum of the KE initial is going to be greater than the sum of the kinetic energy in our final condition, we can go ahead and say that this collision here will be inelastic because we've actually lost our kinetic energy. And how would this loss in kinetic energy actually manifest itself? Well, this loss of energy can be explained by either friction or heat or light or sound that is produced as a result of this collision occurring. So now that we've figured out that this collision is going to be inelastic, let's go ahead and find out what the force will be on the truck as a result of the collision caused by the car. So let's write that down as force experienced by truck. Now if we go back to our previous lesson, we learnt that the force experienced by an object is equal to the change in its momentum divided by the contact time. And in this case, our contact time has been given as 40 milliseconds, which I can go ahead and write as 40 times 10 to the negative 3 seconds, because milli just essentially means 10 to the negative 3, which is also equivalent to 0.04 seconds. Now let's go ahead and look at the change in momentum for the truck itself. So we've got the mass of the truck multiplied by the final velocity of the truck, so VTF, minus the initial velocity of the truck, which is VTI, and that's divided by our change in time, which is T. We know that the truck was initially stationary, so it had no velocity, so that'll be a 0 term. And we know that with the final velocity of the truck, it was moving towards the right at 6.5 meters per second. So let's go ahead and plug our numbers in. So we got 2200, and VTF will remain positive because it was moving in the right direction. So 6.5 divided by the contact time, which is 0.04. And that gives us a force of 357.5 kilonewtons, or I can write that as 357,500 newtons. And because this is a positive number, that means our force will be towards the right, which if you think about it makes sense because the car is moving towards the right and it's about to hit this giant truck, so it's about to apply force in this direction. So I'll call this force of collision. Now what if we wanted to know what the force exerted by the truck was onto the car? Well, if we go back to Newton's third law, we know that when a force is exerted by object A onto object B, then object B exerts an equal and opposite force back onto object A. So in this case, since our car exerts a force towards the right at 357.5 kilonewtons onto the truck will exert an equal and opposite force onto the car, which will be equal to 357 kilonewtons towards the left. And if you wanted to do a quick sanity check in the exam, or a test, and I completely understand that because, you know, these can be like high pressure situations, you could actually go ahead and show this mathematically as well. So we could use the same equation here. We could say force is equal to delta P divided by time, and delta P in this case would be the change in momentum for the car. So let's put in our values. So let's say MC, which signifies car, is equal to the V car final, so final velocity of the car, minus initial velocity of the car, and we will divide that by the contact time. So let's put in our figures. So the mass of the car was 1200 kilograms, so let's put that in. The velocity of the car in the final instance was minus 1.92, and the initial velocity was 10 meters per second, so we'll put that in as well. Our contact time is the exact same, so 0.04, and that will give us negative 357.6 kilonewtons. And this 0.6 is just due to us rounding up that 1.92. It's actually 1.9167 or something if you put it into the calculator. So if you put the exact number in there, you'll get 357.5 kilonewtons, and that'll be negative. And this negative actually works out to tell us our direction, which is left. So that negative signifies the left. So this brings us to the end of the momentum module. I hope you've learnt quite a bit from it, and you can go ahead and use this knowledge in your other questions. Cool, thanks for joining me, and as always, I'll join you at the next one.